For most of human history, progress has followed access to resources: stone, bronze, iron, coal, oil. Each era shaped not just by new ideas, but by new materials. Civilizations expanded where resources were abundant and stagnated where they were scarce. On Earth, those resources are not disappearing overnight, but they are unevenly distributed, increasingly expensive to extract, and often environmentally costly to access. Scarcity, in the modern sense, is less about running out and more about limits of location, energy, and impact. Beyond Earth, however, the picture changes completely. The solar system contains vast quantities of water, metals, and energy-rich materials, often concentrated in ways that simply don't exist on our planet. Today we'll look at where those resources are found, why they matter, and what makes them difficult to access. These are 10 resource-rich locations in our solar system. Number 1. Near-Earth asteroids. Some of the most accessible resources beyond Earth aren't far away at all. Near-Earth asteroids pass relatively close to our planet and require far less energy to reach than deeper targets in the solar system. Many of these asteroids contain water, nickel and iron, and platinum group metals. Water alone is extremely valuable in space. It can be split into hydrogen and oxygen for fuel, used for life support, or converted into radiation shielding. Because of their low gravity, asteroids are easier to mine than planets. Material can be extracted without deep drilling or heavy infrastructure. For early space resource extraction, near-Earth asteroids are often considered the most realistic starting point. Number 2. The main asteroid belt. Between Mars and Jupiter lies the asteroid belt, a vast region containing millions of objects. These asteroids fall into different categories: carbon-rich asteroids containing water and organic compounds, silicate-rich asteroids containing useful construction materials, and metal-rich asteroids with large concentrations of iron, nickel, and precious metals. Some individual asteroids contain more metal than has ever been mined in human history. The challenge isn't abundance, it's transportation. Moving metal from the asteroid belt requires energy, time, and precise orbital mechanics. But the sheer quantity of resources makes it one of the most significant reservoirs in the solar system. Number 3. The Moon's polar regions. The Moon may appear dry and barren, but its polar regions tell a different story. In permanently shadowed craters near the lunar poles, water ice has accumulated over billions of years. This can be converted into drinking water, broken down into oxygen and hydrogen, and used to create rocket fuel. In addition to water, the Moon's surface contains oxygen locked inside its soil, along with silicon, aluminum, and iron. The Moon's low gravity makes launching material into space far cheaper than launching from Earth. Rather than serving as a mining destination for Earth, the Moon is better understood as a supply depot, supporting space infrastructure and deeper missions. Number 4. Mars. Mars is rich in materials that support long-term presence rather than export. Its atmosphere is composed mostly of carbon dioxide, which can be processed into oxygen and fuel. The planet also contains subsurface water ice, iron-rich soil, and minerals that could be used for construction. Mars is far less valuable as a source of exports. but extremely valuable for local resource utilization. Using what already exists on Mars reduces dependence on Earth and makes permanent habitation possible. Number 5. Europa. Europa, one of Jupiter's moons, is covered by a thick shell of ice beneath which lies a vast subsurface ocean. That ocean contains water, salts, and chemical energy sources. While Europa is not a near-term mining target, it represents an enormous concentration of accessible water in the outer solar system. Water in space is not just a resource, it's infrastructure. Europa's distant and radioactive environment make extraction difficult, but its scale makes it significant in the long-term picture. Number 6. Ganymede. Ganymede is the largest moon in the solar system, larger than the planet Mercury. It contains thick layers of ice, liquid water oceans, rock, and metal beneath its surface. Ganymede also has its own magnetic field, which offers some protection from radiation. While extraction challenges are substantial, the sheer mass of available water and raw materials makes Ganymede one of the most resource-rich bodies beyond Earth. Number 7. Titan. Titan, Saturn's largest moon, is unique. It has rivers, lakes, and seas, not of water, but of liquid hydrocarbons like methane and ethane. These compounds are valuable as chemical feedstocks, energy sources, and building blocks for complex materials. Titan also contains vast amounts of organic chemistry, making it one of the richest chemical environments in the solar system. While extremely cold and distant, Titan represents a type of resource wealth that doesn't exist anywhere else at scale. Number 8. The Sun. Not all resources are solid. The Sun provides an immense and continuous flow of energy. Advanced concepts propose large-scale solar collectors, orbital energy harvesting, and beamed power transmission. While these ideas remain technologically challenging, solar energy in space avoids atmospheric loss and night cycles. Energy, not matter, may ultimately be the most important resource we extract beyond Earth. Number 9. Space itself. One of the most resource-rich environments is space itself. Microgravity allows for new manufacturing methods, ultra-pure materials, and large-scale construction not possible on Earth. Rather than exporting raw material back to Earth, much of space resource extraction will support infrastructure built and used in orbit. The value is not just in what's mined, but where it can be used. And finally, number 10, the Kuiper Belt. Beyond Neptune lies the Kuiper Belt, a vast region filled with icy bodies left over from the formation of the solar system. In terms of raw material, it is one of the richest regions we know of. Objects in the Kuiper Belt contain large quantities of water ice, frozen gases such as methane and ammonia, and organic compounds formed over billions of years. Taken together, the total mass of material in this region exceeds that of the inner solar system. However, abundance alone does not make a resource usable. The Kuiper Belt is extremely distant, Travel times are measured in decades with current propulsion methods, and the energy required to transport material from that region makes mining impractical by any near or mid-term standard. For that reason, the Kuiper Belt is not a realistic destination for resource extraction today. Its importance lies elsewhere. If propulsion, automation, and energy generation technologies advance far beyond their current limits, regions like the Kuiper Belt represent a future phase of expansion, not an immediate one. It serves as a reminder that scarcity in space is rarely about availability. It's about reach. The solar system is not short on resources. What limits access is not availability, but technology, energy, and economics. As those constraints change, the boundaries of resource extraction change with them. Earth will remain essential, but it will not remain alone.